Imagine spending millions to build the world's most advanced quantum computer, only for someone to say they can do that on a laptop. It sounds like a completely impossible claim, right? To understand how we arrived at this moment, we have to look at a concept called quantum advantage. This represents a specific crossover point where scientists must prove a quantum machine can solve a problem that no classical computer could process in a reasonable timeframe. Recently, researchers used D-Wave's Advantage 2 quantum annealer to model a difficult class of physics problems called quantum spin glasses. These systems are so disordered that simulating them accurately was considered a primary test for quantum hardware. D-Wave's successful results established a computational baseline that conventional machines were believed to be unable to match. To understand the difficulty of a quantum spin glass, imagine trying to predict the exact movement of a massive flock of birds. Now imagine that every single time one bird turns, it instantly alters the flight path of every other bird in the flock simultaneously. Calculating those interactions requires enormous computational effort. This chaotic information is described by the wave function. The mathematical barrier is straightforward. Adding a single qubit exponentially multiplies the required data. Like memorizing every arrangement of multiple card decks, the storage requirements instantly max out the memory limits of normal computers. Because of this memory wall, these specific simulations were categorized as a task that only quantum hardware could handle. A team of researchers from the Flatiron Institute and Boston University approached the problem from a different angle. Instead of attempting to brute force their way through the data wall, they asked if it was necessary to store every single detail of the wave function. Their solution combined a modern mathematical tool called Tensor networks with belief propagation, an algorithm originally developed in the 1980s for probability analysis. Think of a tensor network as an incredibly intelligent zip file. Instead of forcing a computer to remember every isolated detail, the algorithm identifies structural patterns. It discards the useless information and retains only the critical particle relationships that dictate the actual quantum behavior. By stripping away the dead weight, the required computational power plummeted. They bypassed the physical memory constraints that were supposed to make the simulation impossible for classical machines. The underlying physics problem remained identical, but the mathematical approach changed. By asking a more efficient question, the researchers condensed a massive calculation down to a manageable size. The classical tensor network successfully matched the quantum computer's results. It accurately processed complex 2- and 3-dimensional lattice structures containing hundreds of distinct qubits. And here is the surprising part. Some of these initial simulations ran entirely on a standard everyday laptop. To be accurate, a laptop could not handle the entire project. The most demanding models in the study required heavy-duty CPUs and GPUs to process. But crucially, that is still conventional silicon. Classical technology performed the heavy lifting. The researchers behind the original D-Wave work pushed back. They reviewed the tensor network simulations and argued that the new mathematical approach did not successfully replicate the absolute hardest extremes of their original experiment. This means the case is far from closed. We are watching an active, real-time scientific debate where one team sets a benchmark and another team immediately challenges it. So who do you think holds the advantage right now? This classical comeback does not mean quantum computing has failed, nor does it make the hardware obsolete. Quantum hardware is chasing a moving target. Every leap in hardware capability is met by an evolution in classical mathematics. The two fields push each other forward. Every time a quantum machine achieves a new level of processing power, it forces mathematicians to write smarter algorithms. Every time a classical algorithm improves, it raises the bar that quantum computers must clear. This back and forth results in more sophisticated tools for exploring high-level physics. We gain better methods for solving the universe's hardest problems, regardless of which hardware platform reaches a milestone first. If a clever mathematical shortcut can make an impossible physics problem solvable, what other challenges are we currently underestimating? Let me know your thoughts down in the comments. To keep tracking this race and catch the next major breakthrough as it happens, make sure to like, share, and subscribe. Because as we've seen today, the biggest technological breakthroughs don't always require building a massive, faster machine. Sometimes they come from a smarter idea.